Now the next instrument we're going to look at is telescopes. So the opposite of looking at something close is looking at something far away. So there are two fundamental types of telescopes because we are looking at stuff that is so far away. A refracting telescope, which means refracting means we use a lens and the light goes through it. And a reflecting telescope means we use a mirror of some sort where the light comes in and reflects back into some sort of collector. The largest refracting telescopes is in Yerkes Observatory that had been until recently run by the University of Chicago. This is in Williams Bay, Wisconsin, very close to Lake Geneva, and it was just recently shut down just because it can't compete with the space telescopes and the other ground telescopes that are more radio telescopes and the telescopes in Hawaii that can be much, much bigger due to the limitations of a refracting telescope. The largest optical wavelength telescope that uses reflection is in Hawaii. It's got a 10-meter diameter, whereas the Yerkes Observatory only has a 1-meter diameter. In the next section, we're going to talk about why here size matters. The diameter really matters and how much you're able to see and how much you're able to resolve from the telescope. So here's pictures in Hawaii of the telescopes there. A refracting telescope uses lenses just like we talked about with the microscope. They have a slightly different setup, and the two lenses are separated by the sum of their focal lengths. So that is equal to L for a telescope. So the two lenses are arranged such that the objective forms a real inverted image again for eyepiece, and the eyepiece forms an enlarged inverted image of the first image. So this is the classic telescope that you've seen probably in movies and such. The angular magnification of the telescope then depends on the focal lengths of the lenses that we use. So the angular magnification means basically how much bigger did we make it. So for a long focal length, it looks like it's farther away, but it looks smaller. For a short focal length, it looks much closer. So the overall angular magnification that we're going to get is the ratio of the focal lengths of the eyepiece and the objective. So the angular magnification is particularly important for observing nearby objects. Very distant objects will just be a point of light. But if we want to be able to see the rings on Jupiter, we need a larger magnification. So the disadvantages of refracting telescopes, which is why this one is no longer in use, is that the large diameters are needed to study very, very distant objects. And you can't make a piece of glass that's this big. This thing is 1 meter in diameter. That's 6 feet. That means you can lie on the top of this thing. It's huge. Can you imagine how big of a piece of glass is in there to be able to do that refraction? It's just too much to make that big of a piece of glass. So they're considering reopening this observatory and kind of being run by the public, but it's no longer used for scientific investigations. So the reflecting telescopes, however, what happens is the light comes in from the outside, from infinitely far away, and gets focused into a collector, and then that collector sends light with another small mirror to an eyepiece lens. So here you can make these very, very big and be a perfect piece of glass. So this guy is 10 meters across, it's like 10 yards across. I would love to see this thing someday. So it reduces the amount of chromatic aberrations, and you can just get a much better image than you can with a standard lens. And you can buy a reflecting telescope for home use too. In fact, we have one in Science Hall that we can take out and look at. It looks a little bit different than your classic telescope. Your classic telescope looks just like a long tube, and you look in one end. A reflecting telescope will have a mirror at the end, and you'll have your eyepiece at the side, so you'll view it from the side. So here's kind of what it looks like. This is usually a much bigger chamber, and you look in the eyepiece at the side from this mirror that collects the lights. This mirror is going to be near the focal point to reflect the light through this final lens as an eyepiece. Now we're going to look at a problem where we're going to use these equations for a telescope. The diameter of the moon is this number, so that's going to be our h. The distance to the moon is that number, so that's our p for our objective. Here is the focal length for our objective and the focal length for the eyepiece. To get the optimum length of our telescope, we're going to add that 2.4 plus 0.16, those two numbers to get 2.56. And then the light coming from the moon is basically at infinity, so the image distance is going to be basically at the focal point. That's saying that 1 over f is equal to 1 over p plus 1 over q. This is so much bigger that this is pretty much 0. So in this equation, I'm going to substitute out q for f for our objective. That means h primed is equal to f objective over p times my h value. So that's negative f for my objective is 2.4 meters over 384,500 kilometers times 3,474 kilometers gives us a value of 0.0217 or 2.17 centimeters. So something that's viewable. And then the overall magnification is the ratio of our focal lengths. So 0.16 gives us a total magnification of 15.